All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. It's our last class today. Hooray. Yeah. It's the last class today. I believe it's the last day of classes. Yes. Yeah, it's the last day of classes. So term is coming to an end. I hope that you're all doing okay. I hope that you don't have too many things that are also due in other classes today. I hope you don't have too many things going on today, but today we're going to wrap up the course by talking about page directories and making some connections between paging and file systems, and ultimately being able to see really that the file systems, the file systems that we have looked at in the past, specifically inode-based file systems, they do a lot of the same things that we're going to be doing with paging and page directories. And the two of them are getting so close to each other that you can get to the extent of saying that paging is a way to do file systems, but for memory as opposed to for disks and files. So I've got all the continuing ones here, and I'm not going to restate these. You should be able to describe and explain virtual memory at a high level here. And then today, we're going to finish up, explain the operating system data structures and algorithms used to manage a partitioning strategy such as paging. That's our goal today, is to finish that up. So paging in general, again, the idea with this is we did partitioning of physical memory with base and bounds, and we did partitioning of address spaces with segmentation. And these independently are both very good ideas, and so paging takes both of those ideas and tries to use them together. Where we're partitioning physical memory into page frames, these are the places that we're going to stuff things, and we're partitioning our virtual address space into pages. These are the things that we're going to put into the page frames, and the size of the page frame is the same as the size of a page. So these two units are equal to each other, and this solves the problem of external fragmentation for us. We're either able to find a free spot or we are not able to find a free spot. We don't have to search for something that's big enough to fit the request that we're trying to make. Paging is good because it does eliminate external fragmentation. Again, we can use allocation structures. We can use a bitmap to say, this page is free, you can use it, or this page is not free, you can't use it. But you don't have to find a page that's big enough because all page frames are exactly the same size and all pages are exactly the same size. We are minimizing internal fragmentation. We cannot eliminate internal fragmentation, but we are minimizing it because we have sliced our address space so thin at this point. When we're thinking about 4 kilobyte pages compared to exabytes of address space, losing 2K of data because it's been allocated to a page but not used by a process is irrelevant. It really doesn't matter. It really doesn't matter. So we've eliminated external fragmentation, and we've minimized internal fragmentation to the point that it really doesn't matter. But we ran into some problems last class, which are that page tables are slow. To decode a virtual address from our program counter, we have to access memory multiple times. As an operating system, we're filling up this page table and we're telling our hardware, here's where the page table starts. The page table is going to have to go to memory to translate virtual addresses into physical locations, and then it's going to have to go back to memory to the physical location to actually fetch the instruction that it's trying to load. This is a problem that's ultimately solved by using additional hardware to cache these translations. This is the translation look-aside buffer. But for us, for now, we're just going to say this is a solved problem that we don't really have to worry about from the operating system's perspective. The main problem that we came up with last class that we kind of have to deal with here is that they are way too big. They are way too big. To fit a page table for a 64-bit virtual address space for 4K pages, we're going to have 3 million gigabytes of page table entries, and it's just not going to happen. On top of that, we've got to have this page table for every single process. We have to have a mapping between all the virtual page numbers and all of the the physical frame numbers that we've got. So this is not going to work. It's really not going to work. Our approach now is going to be that if we were able to partition memory and solve external fragmentation. And we were able to partition physical memory and solve external fragmentation and minimize internal fragmentation. If we have this giant page table that itself is internally fragmented, there's the code and heap section at the top and the stack at the very bottom, and everything in between that in this virtual address space is not actually being used by anyone, then let's recursively apply this idea of partitioning and apply partitioning to the page table itself. Let's talk about file systems. Paging and file systems are quite different. They're talking about different levels of that memory hierarchy. So triangle shaped thing, memory that we're talking about with paging is random access memory, and it lives a little bit higher in the hierarchy. And with file systems, we're talking about disks, and it lives quite a lot lower in the memory hierarchy here. And we're also talking about persistent storage versus ephemeral storage. So persistence here is when I turn my machine off, I want my files to still be there when I turn my machine back on again. And ephemeral is it's okay if RAM gets completely emptied when I turn my machine off and it starts up again. I'm okay with that. I want to take a look at this file, proc maps, and take a look at some of the things that we have in our file that represent the address space layout of a process. So I'm opening up here proc self maps, and this is showing us the address space layout for the running instance of the program, the pager less. And some of the stuff that we can see is that we are allocating parts of something. We've got this giant address space, and we're allocating small parts of that. We also have extra metadata about these things. And notably, we have permissions attached to each of these mappings between the file that we've got and the memory that we're mapping it to. We've also got things like inodes, and the inodes here are a relationship between the actual file that's being loaded into the address space. And so that's a little bit of a red herring. Reminder, red herring is like this thing that looks like it's important but isn't actually important in the context of what we're looking at here. The main thing that I really want us to see right now with memory spaces, address spaces, and their relationship with file systems here is that we've got these permissions attached. We have some metadata that's attached to the allocations that we're doing, or the address space mappings that we're doing. Here is the VSFS description of a file system. At the very beginning of our file system layout, the first block in this file system, we've got the super block. This doesn't match exactly with what ext2 did. Remember, ext2 has this 1 kilobyte space at the beginning that's not actually used by anything before we find the super block, but it's still the first thing in the file system. After that, we've got our allocation structures, our inode bitmap and our data bitmap, that represent which inodes are used and which data blocks are used in the file system. And the entire thing here has been broken down into blocks. The super block is a block. The inode bitmap is a block. The data bitmap is a block. Each part of the inode table is a block. Everything is a block. They're all fixed in size, and they're all the same size as each other. Yeah?
I just wanted to ask if I remember correctly, but VSFS is similar to EX2, but without journal, right?
VSFS and ext2 are so close to being the same thing that we can say they are the same thing. ext2 doesn't have journaling in the same way that VSFS doesn't have journaling. ext3 has journaling, but that's kind of like the next version of the ext family of file systems.
After journaling, what did they add in EXT?
Well, the keyword that they added in ext4 is extents, which is way outside the scope of this course. Yeah, yes. Not like exfat, not like exfat. Extents as an EXTENTS. But it's a concept that's outside the scope of this course, and I don't want to bring it up anymore. Yeah.
Out of curiosity, is there a reason that with ext2 there is that 1 kilobyte block of nothing?
That's a good question. I'm sure there is a very good reason, but I don't know what that reason is. Yeah. It's there for reasons. I'm not really sure why they've done it that way. Ultimately, though, we have this big chunk of memory. It's a disk in this case, but it's a big chunk of memory that has been partitioned into fixed size things that we stuff things into. Inodes themselves also have this idea of indirection, references to the blocks. Our page table so far is effectively the same thing as the set of direct block pointers that we have in an inode. Remember that we've got about 15 direct block pointers here, and the direct block pointers in each entry here say it's this block number that contains my first bit of data for this file. It's this block number that contains the next bit of data for this file, and it's this block number that contains the next bit of data for this file. The thing that we're going to look at, and the thing that I want to make really clear that we're trying to make a connection to with the idea of page directories that we're about to see, is that the page directory employs the same idea as an indirect block pointer in ext2 and BSFS. And the idea of our indirect block pointer was that we have 15 direct block pointers, and that's good enough for most files because they are small. But as soon as we get a file that's a little bit bigger than that, we're going to use this indirect block pointer. And an indirect block pointer here is going to say you should look at this block in the file system, and within that block in the file system, you have many direct block pointers, many direct block pointers. But with our file system, we don't allocate these other indirect blocks if we're not actually going to use them for this file. We're only going to allocate them when we actually need to allocate them in the file system and in the disk. So if the file size grows bigger, we may add more indirect block pointers. We might add doubly indirect block pointers. We might add triply indirect block pointers. But until we actually use that space, we're not going to allocate these blocks. And so I'm going to show this really quickly, but I found that this figure was kind of hard to understand, and so I want to restate this figure in my own interpretation of what this figure is trying to accomplish. So I'm going to pop over here to my tablet, and what I have on the left side of my screen here is a page table for a process that's currently running. This is hand-wavy abstract page table, to be very clear, but the general idea is here. On the left side of the table, we have the virtual page number, and these are laid out in the same order as our virtual address space. At the very top, and I've said this before, we've got address 0 in our virtual address space. This is not normally allocated for realsies, but for us, it's good enough. Code starts at the top. Beneath that, we've got 4 more code segments, or 4 more code pages, and then we've got some heap pages. And then we've got lots and lots of pages that have not actually been allocated in this space. So up to 3 million gigabytes of unused pages in this process. On the right side of the table, we have our physical page number. So this represents where in actual physical memory each of these pages are going to be put. And again, this idea of a virtual address space is virtual now. The actual representation of this data in memory doesn't actually look like the virtual address space anymore. It's kind of entirely just going to be wherever there are free pages, I'm going to put stuff. And so the layout here is kind of like, these are all the physical frame numbers that we can have for these different pages, and they're just wherever. They just happen to be wherever in physical memory. We don't have to see any more of our virtual page layout, our virtual address space layout, and we don't have to see physical memory anymore to think about partitioning our page table itself. The key thing that we need to know about our page table is that we've got this giant chunk of internal fragmentation here in the middle. We don't actually allocate anything beneath this right up until we get to the stack at the bottom of this 3 million gigabytes of address space. And so the idea of a page directory here is that I want to partition my page table. I want to partition the page table sort of in the same way that I've partitioned my virtual address space in the first place. My page directory is going to look a little bit like this. It is still a table. It's still a table, but on the left side of my table, the thing that I'm going to use as an index for this, I'm not going to put the VPN itself, so not just the virtual page number, but the prefix of the virtual page number. And I'm going to put values in here like 0, 1, 2, 3, 4, 5, 6, and then ... There's going to be more entries after this, but I'm going to limit it to just having one digit be the prefix of my table. On the right side of my table, these are going to be physical frame numbers. And what these physical frame numbers are going to represent is where you need to go to find page table entries for virtual page numbers that start with this digit. So here, for entry number 0, what I'm going to have, I want to have one single page that represents all of the virtual addresses that I have in this table that start with a 0. I'm going to say that this is going into something like page number, let's say 06, page frame number 06. Where this actually is in physical memory is irrelevant. It doesn't matter. But this then is going to be a page table itself. And it's going to look the same as what we had for our page table initially. The thing that we're using on the left side as an index to this table is now the complete virtual page number. And the thing that we're going to be mapping to is the physical frame number where this page is that actually has this page's data. So here I'm going to have 00, 01, 02, 03, 04, 05, 06, 07, 08, and then I'm going to make this just slightly bigger, 09. No, I'm not going to make it any bigger. We're just going to say that it ends at 08, and then we've got a ... here to represent the rest of the addresses that start with 0. I'll come to you in just a second, okay? Then we're going to take the actual virtual page numbers, the physical frame numbers that we had in our original page table to represent this. And then these ones are not allocated. So they're just going to be entries that are marked as a dash. They're not actually allocated. They're not valid. The rest of the entries here in my page directory are also not marked as valid. And we're not going to allocate pages for those. So the structure that I've effectively got here is that my page directory is effectively the same as an indirect block pointer in my inode-based file system. This is the physical frame number that the hardware should look up to find all of the addresses of virtual page numbers that start with this prefix, that start with the prefix of 0. There are no allocated pages that start with a 1. All of the pages in my virtual address space that start with 1 have not actually been allocated by this process. And so I'm not going to have a page that has page table entries for those addresses. I'm not going to allocate it in the first place. And so partitioning here is going to use that prefix, and it's going to take that prefix, and for the ones that actually have addresses that are allocated in that virtual address space, only then will it allocate these page table entries. Yeah.
I was going to ask related to VPN prefix, but it kind of sold in my mind.
Yeah. So this, I guess, just to clarify, this physical frame number here is going to be to find page table entries. To find page table entries. This one is going to be to find data, to find the actual data of what's at that virtual address. Yeah.
Does the size of the variable size of each VPN increase as the VPN prefix increase?
Well, so that's a good question. Does the VPN prefix size change? The VPN prefix here is what we're using to decide in terms of how much partitioning we're doing. So the reality is that if we had 64-bit addresses, I would probably have like 5 zeros here for this prefix. I'm simplifying this down into much, much smaller than we're dealing with in reality, but it's going to be the first n bits that we're going to use as the prefix for the VPN here. And that number n is going to say how many partitions of our virtual address space that we've got, in the same way that the number n was used to partition physical memory. So what I've got here, and what's important to me about all of this, is that this is approximately equal to indirect block pointers. It's not identical, but it's close enough with this idea of indirection for finding more data for this thing. This structure could also be used with doubly indirect pointers. We could have multiple levels of this directory to have more granular partitioning for our page table entries at the cost effectively of we have to do more memory accesses for every translation that we need to do. They'd have to go through multiple levels of tables to find the address that I'm actually looking for. But again, the speed problems are solved by hardware. The speed problems are solved with a cache, the translation look-aside buffer, the TLB that we have in our system. Are there any questions about this? Yeah.
I would imagine as the VPN prefix increases, the VPN number also increases. So the VPN number can strike up to 3 million, let's say.
So I guess to be clear, the VPN itself, these virtual page numbers, this is a fixed number of bits. Yeah. And what we're ultimately doing with partitioning is deciding how many of the leading bits we're going to use to partition our address space and our memory.
Also,
So like this 3 million gigabytes, this is for a 64-bit address space. I guess if you move to a 32-bit machine, yeah, the VPN size is going to change. But once the architecture has been selected, our virtual page numbers and the addressing space that we have is fixed by the hardware. It's more of a decision on our part to decide how big each page should be. All right, awesome. So I'll post something that looks a little bit like this up to the course webpage later today. Just hold on, don't get up and leave yet. Okay, so at this point, you should be able to virtual memory. We've taken a look at 3 different approaches to virtual memory: base and bound, segmentation, and paging. And we've also now looked at multi-level page tables, page directories effectively, in terms of being able to actually fit an actual address space into physical memory when most of our address space is not actually used by the process that we've got. So the operating system responsibility here is to build these page tables for each process and construct the page table entries, keep the page table base register. So this is page table base register to tell the hardware where the page table starts. This changes to the page directory base register to tell the hardware where the page directory starts. The hardware then is going to have to know in advance how many levels of indirection there are, and it will navigate itself through all the physical memory that we've got for this. But beyond that, it's the hardware's responsibility to do our address translation. Yeah. Yep.
So the left side, like the right side is representing, like you're not using both. It's like the right side is representing the left side.
Yeah, so these are going to be a one or the other, and effectively this is partitioning the table. So modern systems use page directories. There are page tables within the concept of page directories, but we don't use them both like at a super top level thing. We don't have page table for a process and then separately page directories for some other process. We just have page directories for all processes. Yeah. Okay, awesome. So at this point, what I've got is nothing. I don't know why there's nothing there, but now I'd like to move on to review. So a quick ride through our course is that we started with file systems. We started with like, let's remember how C works, and then we started with file systems. Once we finished up with file systems, we moved on to begin to look at concurrency, and then eventually to scheduling, and then I/O and hardware, and then where we're at right now, which is virtual memory. So I've got a number of questions here that that we can work through. I'm still waiting for players.
For some reason, it's not loading.
I'm going to hit Control R. There we go. Okay. You're able to join now? I can put the QR code back if that helps. But I see lots of people joining, so okay, awesome. So I've got questions in this that go back a little bit to file systems, and then we're going to work our way through other stuff. And what I've tried to put into this in between each of the question sets is just a brief moment for you to ask open questions if there's anything that you want to know more about the topic that we're looking at. So between each set of questions, there will be an open Q&A sort of thing. I'm going to get this started. So here's the first question. All right, okay. So this was a long time ago. Clusters versus blocks. Yes, they are different names, but they are conceptually similar in terms of what they are. They are fixed size chunks of the disk. They are fixed size chunks of the volume that we're looking at. So in my mind, those two are effectively the same concept. They're effectively the same concept. Allocation structures, VSFS and EXT, I'll come to you in a second. VSFS and EXT2, they both have this allocation structure for inodes and data blocks as bitmaps. EXFAT also has a bitmap for clusters that represents which clusters are free and not free. Superblock versus MBR, nobody picked that, but this is a superficial difference to me. These are effectively the same thing. These are places where there's metadata about the file system. This one, I'm actually quite happy nobody picked, but that file name directory relationship is effectively the same between these two file systems, where the file name is embedded in the directory itself for the thing that we've got. The main thing that's different between these two file systems, and to be clear, there's lots of differences, but of the 5 that we've got here, inodes and not inodes are really the best answer. The EXFAT file system has much less metadata in it for each file than the EXT2 and VSFS file systems in terms of inodes. Yeah.
Oh, you answered my question.
Okay, awesome. Okay. Okay.
They should all get an A+.
Maybe they will. Now we're moving on to pipes. So that was all I wanted to ask about file systems.
We get one question.
No, there's going to be more than that. For file systems, that was the only one I wanted to ask. Awesome. Yes. Yeah. So I want to give some spiritual credit to linked list and say that, yes, we could use a linked list to implement a queue, but the data structure here that's the best answer is the queue. the write end is enqueuing stuff. The read end is dequeuing stuff. And it's a queue underneath. It's ultimately a queue underneath that represents this, this concept that we have between two different processes for IPC.
What if I accidentally misclicked stack?
If you might accidentally misclick stack, then I guess you just won't get on the leaderboard right now. The next question requires me to show you a little bit of code. And so I'm going to pop over to my terminal here and I'm going to open this. This is the code that I'm showing you for the question. And I'm going to tell you what the question is. And I want to give you like 30 seconds to read this code and think about it. The question is, this code blocks. It gets stuck. Why does it get stuck? I'll give you 5 more seconds to look at the code, and then I'm going to switch to Mentimeter. And then I'm going to try to do some fancy window management to try and keep them up at the same time so that you can see them both. Okay. All right. Okay. So good. I'm really happy that we're mostly picking at the end there. So I'm also quite happy that nobody has selected this one. Writing to std out blocks. Writing to std out never blocks. It never blocks. As far as we're concerned, it never blocks. Reading from a pipe doesn't always block. It can block, but it doesn't always block. Sometimes a pipe will just have data in it. The writer will have enqueued data for there to be data to be read from the pipe. The read end of the pipe is not closed by the child and the parent. These are good things to pick in terms of like, yeah, this is ultimately the core problem. There are ends of the pipe that are open where we're still waiting for something to happen. But the key here is that the right end of the pipe is not closed by either the child or the parent. And so the code structure that we've got here is that on line 5, at the point we're at line 5 here, we've called pipe, and then we fork. So we're duplicating the process control block, and both of these processes have entries in their open file table for both ends of the pipe. The child process is going to start reading, and it will block here. It will get stuck, and it's going to get stuck until our parent is able to start writing stuff to it, and it will eventually unblock. It will write out HI exclamation point. The parent, after it does write, will get stuck on line 17. It's going to wait here. It's going to halt. It's not going to be able to proceed because it's waiting for the child to finish. The child is going to get blocked here because somebody holds a right end open to the pipe. And if anybody holds a right end open to the pipe, that means my read might eventually succeed. Maybe. But the problem here is that, 1, the parent is holding the right end open, and 2, the child itself is holding the right end open. They both have the right end open. And as long as anybody has the right end open, that read is going to block. And now we're stuck in a deadlock here. The child is waiting for the right ends to close on reads, and the parent is waiting for the child to end on wait. But we're stuck. Neither of these are ever going to make any progress here. Does that make sense to everybody? Awesome. Okay. This is a real shakeup. Frosty's at the top. All right. So, are there questions about IPC? Are there questions about file systems? I'm also happy to answer verbal questions. Yeah.
Just a curiosity there. What if the child and the parent leaves the read end open? Is it just
So if the child and parent leave the read end open, it kind of depends on what they do after this stuff. The write end is not waiting for a reader to show up. It enqueues data up until it can't enqueue data anymore because that queue is full, but it enqueues data and then it returns immediately. So it's not going to block generally. If the read end is left open by these and we call exit, it gets cleaned up by the OS. The open file table in the PCB is cleaned up. We exit from the main function and it cleans everything up. If we proceeded to do lots and lots of other stuff, we started opening more files and we kind of like hang around for a long time, we're leaking file descriptors, but that's the side effect. We're leaking a resource, but there shouldn't really be any like unexpected outcome other than I don't have enough file descriptors anymore. But even then, it's only one per process, which is not actually that much. Yeah. Are we all good? Should I proceed? Okay. Whoa, no. Okay, it's fine, Oh, sorry. There is, but I'm set in my ways. Here's the code. I'm going to show you this code now. The question you have seen, does this code contain a critical section? I'll give you 10 seconds with this. This is quite short code. Okay, I'm going to pop back to Mentimeter and I will do fancy window management to try and get this to show up again. In GNOME.
Yeah, like management thing or graphics.
Okay. I'm going to be honest with you. I'm never going to learn how to use it. I'm just going to keep doing what I'm doing. All right. So yes, this code does contain a critical section. This code contains a critical section in a way that's maybe a little bit unexpected. All of the critical section stuff that we have looked at so far, and reminder of definition here, critical section is a section of code that contains a race condition. The critical section in this code is this line by itself. Plus plus is the operation that we saw previously as being the canonical race condition code. It is something that does a read, and then an add, and then a store. And the problem with that ultimately was that we're doing load, add, store as 3 separate instructions, and we can be interrupted in between any of those 3 instructions. This line of code contains a load, and a store. There are 3 instructions here to do all of this. Yeah.
Are the nodes.next, are they supposed to be removed next.next?
No, this will remove the nodes next. So it's going to like take the next here and it's going to stick it out somewhere else. It's not going to be connected to the list anymore.
Well, what's the like node isn't a variable?
Oh man, I'm sorry. Remove next. Okay, fair enough. I will give you some spiritual credits if you said no, because I did a bad job of naming variables. What I do want to show you really quickly is I want to take a look at this thread remove.c. And I want to look at it in a website that's called, it's called godbolt.org. This is somebody's surname. His name is Matt Godbolt, I think. And the software is called Compiler Explorer. And what it does is it will take C code and it will generate assembly language outputs using compilers. And it also does cool stuff, like it will show you like this line maps over to this segment. And what's really neat to me is that if I move these onto separate lines, then we can actually see this is multiple instructions to get next, and this is multiple instructions to get to do the actual storing of the data. So I'm thinking this is 3 instructions. In x86, it's actually like 5 instructions, and we can be interrupted in the middle of any of those 5 instructions. So there's definitely a race condition in this code and a critical section.
It's crazy that people used to write this.
Yes, it is crazy that people used to do that. This one is a type enter. This one is a type enter. And when you're answering this, do all lowercase, no punctuation for the 4 conditions for deadlock. I don't know. So I want to give so much credit to this person. I'm really sorry. I want to give so much credit to all these. Lesson learned, don't use type answers. Don't use type answers. So no preemption. Once I hold a lock, I shouldn't be able to have that lock removed. Mutual exclusion. Once I hold a lock, nobody else should be able to hold the same lock that I'm holding. Circular wait. So there's multiple threads of execution and multiple locks, and they're waiting for each other, and hold and wait. Once I hold one of them and I'm trying to get the next one, I'm not going to give up the one that I'm holding right now. My lesson learned, yeah, don't use type answers. Just don't use type answers. So those are the 4 conditions for deadlock. And our next question is directly related to that. All right, okay. When we break any of the 4 conditions of deadlock, we can guarantee that it will not deadlock. So if I can break mutual exclusion, if I implement locks incorrectly, my code will not deadlock. I can guarantee that it will never deadlock. If I break circular wait, if I reorder stuff, so that was the example that we did in class with deadlock, was we reordered our accounts to try and make sure that they're always going to have lock acquisition in the same order. This is in the textbook, this idea is described as total ordering of locks, to making sure that we're always acquiring them in exactly the same order. So if we break circular wait, we can guarantee that deadlock will not happen. If we break hold and wait, so use try lock instead of lock on the second lock that we're trying to acquire, we can guarantee that deadlock will not happen. But if all 4 of the conditions for holds, the best we can say is that the code might deadlock, maybe. And when I ran that code in class, I had to run it a surprisingly few number of times for it to actually happen, but it didn't happen every single time I ran it. It was just sometimes this might happen, maybe. We can also technically say that the code might not deadlock. If all of them still hold, it might not deadlock, and that is a valid outcome here. This is the most best answer. The code might deadlock. But if we can break any of them, we're guaranteed to not have a deadlock. Oh gosh, sorry. The code is not guaranteed to deadlock, definitely. It's going to be only maybe for what we've got. All right. This one is yep. We definitely need some kind of atomic. It's not necessarily an atomic flag, but we need to have an atomic plus plus operation for ticket locks to work. if plus plus is not atomic, and this is the way that different threads of execution get their ticket number when they show up and try to acquire the ticket lock. If the plus plus is not atomic, two threads might get the same ticket number. So we have to have an atomic operation on this implementation for the ticket lock implementation to work. There's one last question here about threads of execution and concurrency. Did you hit it too fast? No. All right, okay. The answer here is no. If we're doing cooperative multitasking, we don't actually need atomics for locks. Because we're not yielding in the lock. When we're trying to acquire it, we're yielding, but we're never going to have the testing and setting be two separate operations from the perspective of a cooperative task. Assuming we write this correctly, our task will never yield in between testing and setting. So we didn't actually need atomics for the cooperative multitasking part. We 1000% needed atomics for P threads. We need it for P threads. We must have it for P threads because we can be interrupted anywhere. Testing and setting is not atomic. Testing and setting is not atomic. If we're interrupted in the middle of it, we will test. And then maybe somebody else sets. And then we also set. But with our cooperative multitasking, we don't actually need atomics for this if we're just thinking about cooperative multitasking. Frosty has retained their lead at the top. Are there any questions about concurrency and locks before we move on to our next little segment? Just give me a thumbs up if you're going to ask a question. Give me a thumbs up if you're not going to ask a question. My screen froze. I wonder if this is the people in the live stream. If this is someone on the live stream, thank you for telling us. I am going to stop. Okay, so we're streaming again. We should have a screen back up. All right, and that's the only question. So I think I'm going to move on to the next unit here.
The specific rule numbers for MLFQ?
I'm not going to ask you what rule number 5 is, no.
Okay.
But like, and the ordering of the rules doesn't really matter, but you should know what the rules are in terms of how MLFQ works. Yeah, awesome. So if queue time allotment, the time we allow a task to stay in a queue for how much time it's spent on the CPU, if it's too high, then everyone just stays in the top queue forever. If it's too small, then everyone gets pushed down to the bottom queue, always. And because we're doing round robin within those queues, it just becomes round robin. It will immediately become round robin. Here's our next question. It is related to that.
These are all basically the rules.
But I don't care if this is rule number 4 or rule number 5. It's the same thing. It's the same thing. It's the same thing. If we set it too high, if we make S really, really big, then eventually everybody gets pushed down to the lowest level queue. Eventually. Interactive tasks and non-interactive tasks. The non-interactive tasks will get there first. The interactive tasks will get there last, but eventually they'll all be in the bottom queue and they'll just get stuck there. If it's too low, if it's too small, we're just constantly boosting. Every single time we do scheduling, we boost everybody to the top, and we're just doing round robin again. So mis-setting both of those settings will cause round robin ultimately to show up in these things. We'll do one more question, and then we'll end it for today.
I've got a new bus here, and maybe you should have.
Yeah, so MLFQ is fair if all jobs are fair. MLFQ is round robin. MLFQ is round robin, and if we're using round robin and we have preemption, then effectively MLFQ becomes fair. So I'm gonna skip to our leaderboard here, and I'm assuming that Frosty has stayed at the top, so congratulations to whoever Frosty is. That is the end of our class for today.
End of the semester.
End of the semester. I hope that you all have a great rest of your term and summer. I wish you all the best wherever you're going after this. It's been a slice. I'll see you on Monday night. Bye, everyone.